Today we will explore the alternating current, the fundamental concept in electrical engineering and physics that forms the backbone of our power distribution system. I shall begin with by understanding the difference between DC and AC, direct current and alternating current. There are two circuits. One is connected with DC, other with AC source. In the DC source, of course here load, this is load and source. The circuits usually contains are the load and the source. The terminals at the source will carry positive and negative charge, that is electrical polarity. In this electrical polarity only we expect the current flow from one to other direction. The electrical polarity at these two terminals will remain same. This always carries positive, this always carries negative. All the time, it's time. But we see the difference here in the AC source. The terminals, one time it is positive negative, become negative positive. The periodic changes in the electrical polarity between these two terminals, periodic changes. The changes are at regular intervals. That's an interesting point. At this point, with these periodic changes and these electrical polarities remain constant, what difference you are finding in the flow of current and the voltage that you apply in the circuit? The difference here, the current always flows in one direction all the time, and the voltage direction, that is direction of EMF, remains same. The direction of current and voltage as well as magnitude of voltage and current in this circuit remains same. This we can represent by graphs. The graphical representation is x and y coordinates. Take x and y coordinates. Along the x axis you are taking t, time variable, and y axis the current values and voltage values, both. When you draw the graph for the current and voltage, we get a straight line. Both of them will get a straight line parallel to x axis. Shows that the magnitude of the current flowing in the circuit, the current flows always in one direction, no change in the direction of current. And magnitude, the amount of current flowing in the current, that is circuit, remains same, as well as the direction and the magnitude of voltage also remains constant, showing that line represent that the magnitude and direction remains same for both current and voltage in the DC circuit. But what about in AC circuit? In AC circuit, the current and voltage both are vary, periodic. There is a periodic changes in the direction and magnitude of both voltage and current. Periodic variation of direction and magnitude of current and voltage in the circuit. How do you represent? That is, we can understand clearly when you draw the graph. What is the periodic variation of voltage and periodic variation of current as well as magnitude? This is the graph given for only voltage. Same graph for the current as well. Look at that. Here there is a curve upon x. There is a curve beneath x, underneath x. There is curve, similar curves are there. Shows that this is for voltage in one direction, this is for voltage in the other direction. Voltage changes at regular intervals, very important. At regular intervals, voltage direction, that is voltage in this direction, that is one direction, the other direction. Direction changes as well as magnitude. How does the magnitude vary? This is a variation of magnitude of voltage. It increases, reaches the maximum, decreases. That is, rises from 0 to the peak and drops to 0 again at this point. And the reverse direction here increases from 0 to peak and again drops to 0 in the direction. This is some regularity, the symmetric wave we get. And this wave is repeated, same wave is repeated. That is the flow of current and voltage, variation of voltage and current in the circuit. Same wave of same symmetry, that is same size, same length, the repeating of this with time between these two terminals. That is a kind of the current in the AC circuit. And why this variation like this in this case? Because AC is generated by rotation of magnetic field with respect to a coil, electric coil, where electricity is generated. Rotation of magnetic field or rotation of the magnet. During this rotation, the magnetic flux, what is that magnetic flux? I mean, the magnitude of the magnetic flux and the direction as well, it varies with time like this. In the same pattern, magnitude of the magnetic flux and the direction changes like this. And the electricity is generated because of change in the magnetic phase. In the same fashion, electric current is generated. That is the reason we get always a wave like this, symmetric wave like this. This is a wave for the voltage. And what is a wave for the current? Similar curve we get. But here we represented here the same graph for voltage and the current. There is no difference, similarities are there. Smooth curve, the difference here one bigger and smaller. And blue line for the current, yellow line for the voltage. Both of them have seen that this is one curve, that is voltage and current, one cycle or one wave. There is a wave now, one wave. The same wave is repeated. There is one more wave and one more wave. It is repeated with time. That is a kind of variation of voltage and current in this circuit between the two terminals. And interestingly, point is that, and the point of that is a peak value and peak value, zero value. These peak values and zero values between them, these values of this are getting always coincided. At every peak, see that these values are coincided. These zero values are coincided. And these peak values are coincided. Look at that. Showing that these waves, that is current wave and voltage wave, are in phase, in the same phase. And this equation or this graph, what is that? This graph wave graph is similar to a sinusoidal wave in mathematics. In mathematics, we have a sinusoidal wave. That sinusoidal wave is the same as this. It is, we can refer this wave to a sinusoidal wave. AC current, AC cycle, AC generation is similar to sinusoidal waves. The wave form as sinusoidal wave. This is a graphical representation of sinusoidal wave, and this is a mathematical representation of sinusoidal wave. V is variable like this, and Vm is a peak value. Vm is a peak value, that is a positive value, highest value, negative value, same value. Vm, once positive, other time negative, peak value. This is constant. Constant into variable. Sin theta is a variable. Sin of this theta, variable. So V is variable. Sin theta means, what is theta? Theta in this case is omega t. Theta is omega t. What is omega? Omega is an angular frequency. What is meant by angular frequency? This electric current is generated by rotation of magnet with respect to a coil. How many times the magnet is rotated in 1 second is called as angular frequency. Angular frequency. In this graph, you can write this omega. Here theta means, here in terms of angle or radians we represent. So every point on this line, either in terms of t or in terms of radians. So every point has some value of radians or angle and some value of t, any point here. And total angle from here to here, we can refer it as 2 pi, that is 360 degree. And total time taken from here to here, it is called capital T, that is small t becomes capital T from here to here. Time period. So this length in terms of t is t, this length in terms of radius is 2 pi. So it is 2 pi by d, angular frequency. We can write V equals sin of omega t. Variable. T is variable, this constant. Accordingly, V changes like this, sinusoidal wave. This is for the voltage. And what is for the current? Same equation for the current as well as. This is here. Same sinusoidal wave. Therefore, we have the equation for the current. The current is variable, that is I is a variable current in AC, V is a variable voltage in AC circuit. I equals Im sin omega t. Im is maximum value or peak value. Vm is maximum value or peak value voltage. These two are sinusoidal equations. Equation for the sinusoidal wave. Periodic variation. For one cycle, there is a variation for both identities. To understand clearly about the sinusoidal wave, I will go a little deeper into that. Just to understand the sinusoidal wave, I will draw this graph for this. This is graph for one cycle. One cycle. Let me divide this into 4 equal divisions. That is, from here to here, 1 division, 4 equal divisions. One more division, one more division, one more division. That is 1/4 of it, of 3/4 of it, and 1/4. From year to year, year 0, from year to year, what is the value of t? So write the t value. That is t is general. This is t period. Let us calculate what is the sine of the angle at every four. I have taken the 4 points. Sine of the angle when t equals 0 here. When t equals 0, that is v equals vm into sine omega t. When t equals 0, sine 0 it becomes. Sine 0 means 0. V equals vm. V equals 0, sorry. 0 into vm is 0. Let me take at this point and calculate what is voltage and sine of the angle. That is, when t equals, that is t by 4, 1/4 of t. Here. So write into the equation sine of omega, this is omega, and t equals pi by 4. Simplify, you get pi by 2. Sine pi by 2. That is sine of the angle is sine pi by 2. Sine pi by 2 is 1. 1 into Vm is Vm. That is a peak value, maximum value. Similarly, we can do the calculation at this point. It is t equals t by 4, half of the period. Substitute in this equation, t is t by 2, simplify, you get sin pi. Sin of against is pi, sin pi is 0. 0 into Vm is 0, voltage is 0. That shows the voltage is 0. Here, voltage is maximum. At this point, what is t value? T equals 3/4 of the t. Write into the equation, simplify, gets sine of radians is 3 pi by 2. You know that sine of this angle is -1. -1 into Vm is minus Vm, is negative value, peak value. And finally, we calculate, if we do so that it is t equals t. Here t equals t. Into the equation we get sin pi, sin 2 pi. Sin 2 pi by sin 2 pi is 0. So v equals 0. Look at that, the angle variation, it is 0 to increasing pi by 2. That is increases radians like this. And voltage, in terms of sine of, in terms of radians, how it changes radians. 0 to pi, pi to pi, pi to 3 pi to 3 pi to 4 pi. There is a increase in radians and there is a variation of voltage in sinusoidal curve. Just to understand this in deep, to understand the sinusoidal wave, I will do this brief discussion about this. Now, into this, what is that? The AC, when you apply AC to resistor like this, a resistance carrying, carries resistance, a resistor like this, what do you understand that? When you apply this AC voltage, we know that when DC is applied, V equals IR. DC current voltage, the voltage and current remain same. In accordance with Kirchhoff's rule, that is closed circular, that is a source and load. That is source and only one source, one load. They are equal, left hand side. Source equals load. Total load. So this is what for the DC. What? When you apply AC, but when you apply AC, voltage is variable, current is variable. What is the equation for variable voltage? What is the equation for variable current? Equation for variable voltage is this, V equals this, not constant. And equation for variable current is this, it is not constant. Substitute in this equation. This is equal to this one. This equals this one. And simplify. this sin omega t cancel, and Vm equals IMR, that is for a peak value. Look at that, this equation is similar to this equation. I mean, this is for DC current, this is for the AC current. So AC and DC obey the same, that is Ohm's law in this circuit. Whether you apply DC current or AC current, follow the same Ohm's law. This is Ohm's law is okay when you apply to a resistor. What about the energy transfer, the energy transmission or power dissipation or power transmission in the circuit? Here the power transmission or energy transmission, we take what is that, the current or voltage. What current? But current and voltage are variable. I have to take a mean value. Variable means you have to, if there are variable values, means you have to mean of the values. The exact value is the mean of the values. One such mean value is average value, whether current or voltage, high AV or VAV. Can take. What is that average value? Average values, you see that there are number of values are there. Current values. That is, every point they have values, positive values, again the negative values, number of values. For all those values, numerous n number of values, all of them you have sum up and divide by total number of values. When you do so, equals 0 for one cycle. The cycle values of variable contain both positive values and negative values. When sum them up, we get 0 mean value. We get for the same, what is that? V average also 0 for one cycle. If the current mean value is same, does it mean that the power transmission or the energy transmission is 0? No. There is a transmission or dissipation of energy at this resistor. What is dissipation of energy? Some amount of electric energy changes into heat and liberated and come out as heat energy. That is called dissipation of power in resistor. So that is the dissipation. That means there is some current and voltage consumption is there. What is that current you have to take? That current, some other mean value you have to choose. You have to choose some other mean value. There is in mathematics, you have so many mean values are there. What is another mean value is RMS value. That is one more mean value, effective mean value it is in mathematics. IRMS or VRMS. IRMS or VRMS. What is the meaning of RMS values? Here we take these mean values. That is, all the values, square them, sum them, divide by the same number, what number you have taken, and take the square root of the entire thing. That is known as root mean square value. That is also a mean value. This mean value is effective value. In other words, when you find this value, it is not 0. It has some value, mean value. What is the mean value we get? That RMS value, if you do so by using this equation, we get Im divided by root 2. What is Im? Peak value, current, peak value of the current. Divided by root 2 is constant, this root value constant. When divided by root 2, we get this. What is 1 by root 2? IRMS is equal to 0.701 into Im. 0.707 I into Im, we get this. Some mean value we get. Since voltage also follow the same concept, so for voltage also we can write this equation. What is that equation? V RMS. Root means square value of voltage is equal to your peak value of voltage divided by root 2. It is same equation. Voltage value. It is maximum value, RMS value. The peak value, RMS value. Peak value, RMS value. RMS value is equal to this. So, if you use, what is that? We are using voltmeter and ammeter, and the sets are different for DC and AC. So, what the voltage, a voltmeter or ammeter used to record the current in the AC meter, it gives this RMS value, this into this. And the voltage, what is recorded using, that is the voltmeter, especially for AC current, we get this value. This is the equation applicable. RMS is RMS value, that is this into this. So this RMS value is used. There is some current, net current, some mean current is used, consumed in the current. It is in the form of energy transfer or energy dissipation. So that was an example, I will give example. Here, when you calculate the RMS value of voltage like this, V RMS is equal to, this is a constant value, into suppose 170 is the peak value of the voltage. If the peak voltage of the AC, what is applied here, suppose it is 170, what would be the RMS value, that is mean value, RMS value of this voltage? It is 120. What does it mean? That is mean value is 120. That is 120 is effective current. To this circuit, if you apply DC voltage of 120, what amount of power dissipated by this R? It is same. When you apply this circuit with AC voltage, the AC current of peak value 170, AC volt, AC current of peak value 170, same amount of power dissipated, because the correlation in terms of current, that in terms of voltage, in terms of current, if the source of AC current applied to this circuit, your peak value, suppose peak value is 10 ampere, 10 amperes, what is the RMS value? RMS value is 7.0. If you do the calculation, 7.0. That is RMS value, mean value of the current is 7.0. This peak value, this current is used. That means when you apply the DC current to this resistor of 7.07 ampere, same amount of energy, that is power dissipated, if you apply the AC source of 10 amperes to this, that is effective current and effective voltage, clear that. Doesn't mean that in every cycle it is getting cancelled. There is a net voltage, net current, it is used up in the circuit. If you use AC, that is a speciality of the AC. And it is power dissipation equation. Usually we call this power dissipation. Here it was given for the DC voltage, that is VI, in terms of voltage and current, in terms of current and resistance, apply Ohm's law. In terms of current, in terms of voltage, V square. You can use any one of the equation. Now we are using to calculate the power dissipation. What value of voltage you have to use? RMS value of the voltage. What value of I? RMS value of AC is used. Similarly, RMS value of I, RMS value of V is used for the calculation of power dissipation when AC is applied to resistor. and myself. This is regarding the AC. When the AC, that is the complete description of AC, when the AC is applied to a resistor, and what is the concept involved? And this AC, you can't use DC all over. AC is fine. That is, I said already, a backbone of our power distribution system. This AC is easy to, what is that, change the voltage, step up and step down. These are important in the transmission and distribution. That is why AC finds more useful than DC in the production, transmission and distribution. And DC is of course useful at some other, that is what, electronic devices where your battery is using, or any other devices. Can DC also then finds applications. So this is the importance of AC. Thank you.